Now, there's another method that you can use to solve systems of equations that works in well, it works in a few cases, but in particular, you've probably seen it in the case where you're working with uh, two equations and two variables. So that's the example that I'm going to use. So let's say you had uh, two equations and two variables, and you can see that's what I've got here. I've got a linear system of two equations in the variables x1 and x2. This example is kind of already written out, so we're going to fill in a few details, but we'll go through it line by line. So what I really want to remind you of is that you can solve these systems graphically. And it's not necessarily the most practical method to use, but it is very useful for theoretical purposes, for gaining an understanding of what's going on here. So the first thing I want to point out is that we can rewrite both of these equations so that they're in slope-intercept form, where we treat x1 as the independent variable and x2 as the dependent variable. So what I'm going to do is I'm just going to rewrite them or solve. I basically just isolate for x2 over here. So for the first, I'll number this as equation 1, and I'll show some work over here. So I've got x1 minus 2x2 is equal to negative 1. So if I just solve for x2, I'll have this. So negative 2x2 is equal to negative 1 minus x1. Now, if I divide both sides by negative 2, or multiply both sides of the equation by negative 1/2, I'll end up with x2 on the left-hand side. On the right-hand side, I'm going to actually reorder the terms. So I'm going to end up with 1/2 x1, because if I multiply negative x1 by negative 1/2, I'll end up with positive 1/2 x1. And then the negative 1, this term hasn't been dealt with. If I multiply that by negative 1/2, I'll end up with positive 1/2. So that's where this equation comes from, the equation that defines a line L1. So you can see that I've assigned, this is the equation of a line in the x1, x2 plane, and I've just given it a nickname L1 here. That's all that's happening. But where did this equation come from? It just came from this equation using these steps. And we can do the same thing for equation 2 over here, which I'll label as that. So what happens if I've got negative x1 plus 3x2 is equal to 3. I'll solve for x2 again. So I'll add x1 to both sides of the equation. So I'm going to have 3x2 is equal to 3 plus x1. And then I'll multiply both sides of the equation by 1/3, and I'll get x2 is equal to 1/3. I'll reorder the terms as well, so the x1 term comes first. So I've got 1/3 x1 plus 1. So that is where the equation for the line L2 came from. So just to recap what we've got a system of two equations and two variables. The idea is each of those equations represents a line in the Cartesian plane if we plotted it on the x1, x2 axes. And if you give those lines names, L1 and L2, and you graph them, you're going to see exactly what we have in this picture. Right? You're going to have two lines, and they're going to look something like this. And you see they actually have a point of intersection. There is a point here where the two lines intersect. Now, this is a nice case because you can actually see what the coordinates of that point are. The x-coordinate of that point, or the I should say the x1 coordinate. We're not dealing with x-axis and y-axis here. We've got the x1 axis and the x2 axis, so I should be careful. So the x1 coordinate is actually 3, and the x2 coordinate, you can see, is actually positive 2. Okay, so the point 3, 2 is the point of intersection of those two lines. A point of intersection actually corresponds to a solution to the linear system. You can check that if you actually plug in 3 for x1 and you plug in 2 for x2, you can check that that is actually going to satisfy both of those equations. So what you could do is you could actually formally say you've got a solution to this system. You could say, let's write it in column form, x1, x2 is as a column. We're going to have 3 for the x1 variable and 2 for the x2 variable. And just to be clear, so that's a solution to this system. So that's what it means to solve a linear system using the graphical method. And like I said, we got off lucky here because sometimes when you get this point, it may not be so obvious what the coordinates are. This example was kind of cooked up so that the coordinates would be nice and easy to recognize. But if the point were moved just a little bit, it might be very difficult to see what the values are. So this is not so useful necessarily for in practice to actually solve systems in general, but it is really nice for theoretical purposes, as we'll see in just a moment. So there's an exercise right below, and I'll ask you to do this on your own. Just plug the values into the variables in each of the equations in our linear system, and make sure that both of the equations are actually satisfied when x1 is equal to 3 and x2 is equal to 2. So basically, just check that what we found genuinely is a solution to the system.